Oh, hi everyone. Thanks for coming to my talk. I will going to show you a constant factor approximation algorithm for the Nash Social Welfare with some modular valuations. I'm Wenzheng. This is a joint work with my advisor, Vondrak. So let's begin with the definition. Nash Social Welfare is an allocation problem. We want to allocate indivisible items to m indivisible items to n agents. And each agent has a valuation function. And we want to find an allocation that is both fair and efficient through maximizing some objective function. For example, for efficiency, we can try to maximize the summation of all valuation functions. That is often known as a social welfare problem. As for fairness, one popular choice is to maximize the minimal. The famous Santa Claus problem is a special case of this. So to balance between fairness and efficiency, here we will try to maximize the geometric mean of all valuation functions, that is, which is between the summation and the minimal. Okay, so, well, of course, we cannot hope to solve this problem for arbitrary functions. So in this talk, we will assume, as in the title, we will assume it to be monotone submodular. We will say later that actually, in some sense, this is the largest nature class we can hope to get a good solution, actually a constant approximation. Okay, so first let me, but before that, first let me remind you what is a submodular function. We call a function f submodular if and only if for any set S and T, f as union T plus f as intersect with T is at most fs plus ft. Another maybe more intuitive definition is through marginal values. A function is submodular if and only if the marginal value of any element is not increasing when you have more elements in your set. Okay, so far is the definition for Nash Social Welfare problem. Unfortunately, this problem is known to be quite difficult. More specifically, it's APX hard in general, and even if with only 2 players, it's still NP hard. So that means we can only hope for constant approximation. However, like constant factor approximation, even for the additive case, is still highly non-trivial. Only a few years ago, it was discovered in a breakthrough result by Kohler and Gaxelis using like a very interesting method called spending restricted market equilibrium. And later, Anari et al., they also achieved constant factor approximation by a totally different approach using theory of real stable polynomials. The current best, the state-of-art approximation ratio is 0.69 using price and wave freeness due to Baumann et al. But for like broader classes, very little was known. Like until very recently, we only know constant factor approximation for piecewise concave valuations and budget additive valuations. As for some modular valuations, the ratio was linear in a number of agents. So it's much far away from being constant. And very recently, like Garge et al., they proposed a new method combining matching and concave relaxation. And they use it to get a constant factor approximation for a class of valuation function called reduce function. We won't need the definition of this class in this talk, so you can just say, and you only need to think it as a subclass of submodular functions with some special like polyhedral formulation, and our result actually builds upon their framework. Okay, so let me introduce our results. We show that there exists a constant factor, actually 380 approximation algorithm for Nash social welfare with some modular valuations in the Oracle model. Just note here that we didn't try to optimize the constant, but we believe that it will still be a triple-digit number using our method. Okay, and as I mentioned earlier, like submodular function, like submodular function is the largest natural class that we can hope to solve with constant approximation. That's because there are hardness results showing that in the Oracle model, it's impossible to get constant approximation for the sub-additive or even fractionally sub-additive valuations with polynomially many queries. Okay, so okay, and okay, so then let me introduce our algorithm. First, to get some intuition about our algorithm, let's first take a look at why the naive relaxation for the additive case fails. Okay. So first, we relax the assignment such that you like it is the most naive way, like you can allocate all the items fractionally. First, it's not hard to say that the integrity gap of this program is unbounded. For example, if there is just only one item, but there are n players, the answer to the original Nash social welfare problem should be 0. However, you can still get a positive value from this program. But if you think but if you think more carefully about this program, okay, you'll find out actually it seems like bad things only happen when all the agents are competing for a few very high value items. So based on this intuition, it's very natural to ask, can we identify a few high value items, assign them integrally, but for the remaining items, just fractionally, like this naive relaxation? Will this approach work? Okay, and that's actually almost exactly what Garch et al. Do in their like new matching based approach. Okay, so in the step 1, more specifically, they find a matching. They compute a maximum matching between agents and items, and all the they call all the matched items as high value items. Okay, and in step 2, like they try to like find a fractional solution on the remaining items, like with a fractional assignment by replacing every valuation functions by their concave extension. After the first 2 steps, it's very natural to think then we need to run the fractional solution, right? As we have seen in the last slide, we cannot like hope to fully run the solution because the gap is unbounded. But here is an important observation. That's a key. is that actually we only need to partially run the solution to make just to make it sparse enough. Intuitively speaking, items in M prime should be less valuable than the matched items, than the high value items in step one. That means if there are only constantly many non-integer items assigned to each agent, on average, we will only lose a constant factor even if we just arbitrarily assign those fractional items. That's an intuition. In the real algorithm, for some technical reason, we still need step 4 to recompute the matching. Okay, but at least that's the algorithm. But at least we can see that in the high level, at the high level, this approach doesn't depend too heavily on the class of the valuation function. However, in the real algorithm, this still needs some additional property to implement each step. Like more specifically, there are two limits to their approach, to their actual algorithm. First, they were trying to solve this program exactly. That means you have to use the concave closure of this valuation function. But it's well known that we cannot evaluate the concave extension for general submodular functions. That only works for a special subclass called growth substitute functions. And second, to sparsify the solution, they require some polyhedral properties of the function, which further restricts the class. So if we want to generalize this matter to some modular functions, we need to come up with a new relaxation of the valuation functions and try to solve it approximately. And moreover, we also need to sparsify find a more general sparsification technique. Well, at last, we also need to combine the sparse fractional solution with the initial matching. But fortunately, this part we can directly borrow from their paper with just a very little change. So we will focus on the first two steps. Okay, for the first issue, we will use a relaxation called multilinear extension. For any, let me define first. For any submodular function v and a fractional assignment x, we define the multilinear extension to be the expected value of random set S, such that S includes element J independently with probability Xij. Okay, it's known that from early work that although multilinear extension is not a concave function in any direction, but it's concave in all the non-negative directions. So based on that, people invented a type of algorithm called continuously greedy algorithm to solve problems like social welfare, and also this type of algorithm, type of problems approximately. But unfortunately, it's a multiplicative approximation. But here, what we really want is an additive approximation on the log scale. So how do we solve this? The solution is just to run the algorithm iteratively. So I will skip the details here due to time constraints, but we can prove that after log n many iterations, we can reach a solution with, as long as as long as we are not close to optimal, then we can always make some progress in every iteration. And we can prove that after log n iterations, we can get the additive approximation on the log scale. So now for the sparsification, one easiest solution is just to run the fractional solution randomly. Let agent I gets item j with probability xij independently. So after all, the multilinear extension is defined in exactly the same way. So it makes sense to also run like this. But of course, it cannot work due to for any submodular function because the integer gap is unbounded. So, but interesting questions to ask is, when does it work? Or equivalently, we can ask, just when does it concentrate? So we know that from like one general principle from concentration theories that concentration works if individual contribution are small. So applying that principle here, we can prove that if a submodular function is theta Lipschitz, it will concentrate. Or in another word, if the marginal value of each item are small, the randomized rounding concentrates to its expectation. Okay, with this observation, the rest of the algorithm is actually quite straightforward. We can keep all the items with large margins contribution unchanged, and only randomize round those items with small margin contribution. By the properties of submodular functions, we know that there cannot exist too many elements with very large margins. That means this partial rounding will indeed give us a very sparse solution. And combined with the previous arguments, we know that that resolves the two issues. Okay, so that's how we. Let me just maybe end with some open problems. The first one is quite obvious. Maybe straightforward. It's quite straightforward. As I mentioned earlier, the current best ratio for active case is 1.45. On the other hand, our ratio is triple digit. Even with some even if you try to optimize the constants, like it will still be a triple digit. So there is a very large gap in between. Can you find like maybe some new ideas to improve the constant? Second, can you find a good approximation for the weighted geometric mean of all valuation functions? As far as we know, it's still open even for the additive case. So we believe that it may require some completely new ideas to make progress in this problem. It will be very interesting if someone has new ideas on this problem. And that's all of my talk. Thanks for listening.